So now we want to compare, now we want to find and compare the computational complexities of the sorting algorithms. So how many competition or how much competition does each of these algorithms take? So if we have this array to sort and we are going to use bubble sort. So in the first iteration, bubble sort is going to make 1, 2, 3, 4, 5, 6, 7 comparisons. So 7 is actually n minus 1. So we have 8, 8 values. So we need to compare. We need n minus 1 comparisons, which is 7. Then we have uh, after the comparison is made, we have so now the bubble sort makes 1, 2, 3, 4, 5, 6 comparisons. Then after the comparisons are made, 2, 4, 3, 10. So then in the next iteration, bubble sort makes 1, 2, 3, 4, 5 comparisons. So at every iteration, the number of comparisons being made is decreasing by 1. So at the first iteration, the bubble sort makes n minus 1 comparisons. Then it makes n minus 2 comparisons. So at one time, it only becomes one comparison. So the total number of comparisons being made here is n into n minus 1 by 2. So this is the number of comparisons we need to make at to sort an array with bubble sort. So this is a fixed number because bubble sort cannot detect if an array is already sorted. So whether an array is sorted or not, it always makes this amount of comparisons. So the best case complexity or worst case complexity for the bubble sort is always the same, which is n into n minus 2. Um, the algorithm is bubble sort, and the best case complexity is and also it is also the worst case for bubble sort. So we have seen that the best case complexity and the worst case complexity for bubble sort is always the same. So this is the average case complexity of the bubble sort algorithm. So if you want to sort this array using selection sort, so notice that um, this algorithm too doesn't understand when the array is already sorted. So every time, at first, the algorithm will find the max of this whole array. So that will take n comparisons to find the max. Then, uh, then it takes one swap. So we can say it is almost roughly n plus 1 computation. Then, since the swapped value is um, since after the swapping 12 will go to this place, so now we have this array to sort. So to find the max of this array we need n minus 1 operations, and then we make one swap, so which is this. So previously we needed n plus 1 operations, now we need n operations. So then when we sort this array, we make n minus 1 comparisons and then one swap, which is n minus 1. So every time the number of operation being done is decreasing by 1. So at some point this becomes 2 1. So the sum of n plus 1 n down to 1 is n plus 1 into n plus 1 by 2. So this is roughly called n square or n square by 2. Uh, so the best case or worst case both for selection sort is the same, which is n into n plus 1 by 2 or n plus 1 into n plus 2 by 2 or n square by 2, it doesn't matter. So that's right. Then uh, we find the computational complexity of insertion sort algorithm. So insertion sort is a bit different. So if we had some already sorted array, then it would just make n comparisons. The first, so it will compare 2 with 1 and see that they're fine. Then it will compare 3 with 2 and see that 3 we cannot move 3 any left. Then we compare 4 with 3 and find that we cannot move 4 any left. Then we have 5. We compare 5 with 4 and we find that we cannot move 5 any more left. So this is the best case that can happen in a selection sort. So in the best case, we need just n minus 1 comparisons, which is almost equal to n when n is sufficiently large. So we call the best case complexity for um, the best case complexity for insertion sort is n. So actually the worst case happens when the array is sorted but in the opposite order. So let's say we want to sort this array from the smallest element to the largest element, but it is already sorted in the opposite order. So when we consider 5, it is sorted. Then we consider 4, then we have to swap 4 with 5. Then we have 3, we compare 3 with 5, and then swap 3 5 and swap 3 with 4. Then we have 2, then we compare 2 with 5, we swap 2 5, then we swap um, 4 and 2, so 2 4. Then we swap 2 with 3, it becomes 2 3 4 5. Then we have 1, then we swap 1 with 4 5 and 4 and 3 and 2. So in this case, notice that how many comparisons are being made. So we compare 4 with 5 and swap. So that is, if you compare 4 with 5, the comparison is one operation and then the swap is another operation. Then we compare 3 with 4 and swap. Then we compare 3 with 5 and swap. So at first we needed 2 into 1 operations. Then we needed 2 comparisons and 2 swaps. So 2 into 2. Then we needed, for 2, we needed 3 comparison and 3 swap. So 2 into 3. Then for 1, we needed 4 comparisons and 4 swaps. So 4. So starting from 2 into 1, 2 into 2, we arrived at n minus 1. So this is the amount of computation that takes place. So in the worst case, the So the sum of these numbers starting from 1 to n minus 1 is n minus 1 into n by 2, and we have a 2 here already, so this will cancel out and we have n into n minus 1 operations. So that is the worst case complexity for selection sort. So we find that the selection sort is always better than the other two algorithms, because even in the worst case it does less computation.